So why do we use statistics for neural data? Well, there's like a bunch of neurons, so we have to use statistics to give an overlook on those sheer number of neurons. And also, actual data is quite noisy, so in order for us to kind of look through those, we have to utilize statistic. And these are just so each spikes are just represented as this one of the short line according to this timeline, and they have 25 trials of the same thing represented in this different figure. And that kind of data we are seeing here is in real life. We could see, for example, like a customer arrival to Highway or Chick-fil-A or something, and they're kind of arriving at some time. And this is pretty common shape of data. So we call this a point process, as the only thing that matters is the point, the time in which they had occurred. So moving on, so we call it a point process. So membrane potential recording is changed into a raster plot that I showed. We can put it in mathematical format, where Ti is like the time in which the first or whatever first, second, third spike has occurred, hence T. Yeah. What we're going to do is that it's the number of bins in window of length T. So the M is the size of the dt. So in a given time T, the bigger the size of the bin, there are going to be less number of those, right? So M represents the number of those bins, and the more number of M, the dt, the size of the bin, is going to be smaller. So that's why I have this kind of relationship. So if you divide the time by the size of the bin, you'll get the number of bins, M. And the probability of firing in the bin size of dt, which represent P, is equal to this. We call this this is a probability constant, and then dt. And the bigger the dt, the bigger the probability, so that it makes sense. And we can represent, since dt is equal to t over m from this equation, you can put it as this gamma t over m. And this equation makes sense as well, because P is representing, so the probability of K event in the window size of T, because the P is the probability of firing happening in that decay, and 1 minus P, and then M minus K, and the probability of not happening, basically. For Poisson distribution, the variance and the average is the same, so I'll put it as a Fano factor, just put them on top of each other, and then if it's one, it could be a Poisson process, although it doesn't necessarily mean just because the Fano factor is 1, it is a Poisson process. And we can see here mean and variance, and it kind of shows like a sine is like the angle of 1, and then we see that it's kind of similar to the Poisson distribution. And we have this t, the inter-spike interval, and like we can it's an exponential function if you like solve it out. And exponential, it just goes like it's like approaches like exponential approaches 0 since it's negative. But in real life, it's not really. It doesn't really make sense because after that means if it was just pure negative exponential function, it would show more like that. But at the beginning, there's a decreased chance of probability at the beginning. I mean, that makes sense because because neuron doesn't actually fire like right after each firing, so we have some refraction period, and that's what is taken accounted for in this actual data. So what we can do is that for each trial, so what we can say is that for each like RASP like a figures, we can the number of spikes that we'll have for each trial can be distributed as a Poisson's distribution. But once we have a number of spikes for each trial, we have to know where to put those spikes along the timeline, and that can be determined by, or not determined, but more of described by the exponential function, exponential inter-spike interval function.